Hello, everyone.
Good afternoon, sir. Good afternoon, Amber Habib, sir. Can you hear me?
Hello. Yes, I can hear you.
Sir, we'll just wait for 5 more minutes and then we'll start the session, sir.
Okay, yeah, that's right.
Good afternoon, everyone. I welcome you all for the fourth day of 1 week online international E-Symposium on modern mathematics. This celebrates Mariam Zahani's birth anniversary. Now I welcome Sunita to introduce today's speaker, Professor Amber Habib sir, to you all.
Thank you, Shweta. Good afternoon, one and all. This is Sunita, Assistant Professor, Department of Mathematics and Statistics, Raja Bahadur Venkatramma Reddy Women's College. It is my pleasant privilege to introduce today's resource person, Professor Amber Habib sir. Amber Habib is currently a professor, Department of Mathematics, School of Natural Sciences at Shivnadar University, Delhi. Professor Habib did his MSc integrated course in mathematics at IIT Kanpur and PhD at University of California, Berkeley. These were followed by postdoctoral positions at the Harish Chandra Research Institute, Allahabad, and the Indian Statistical Institute, Bangalore Center. His research interests include representation theory and mathematical finance. For over 20 years, he has been involved in efforts to make mathematics education at school and college levels more interesting and fulfilling through special topics, projects, and an appreciation of the myriad links of mathematics with other disciplines. This began during his time as a teacher at the St. Stephen's College, University of Delhi, and was his main focus during the years he spent with the Mathematical Science Foundation. He has also served several times as a resident faculty for the Mathematical Training and Talent Search Program sponsored by the National Board for Higher Mathematics. Sir has received the Shivnadar University Faculty Excellence Award for excellence in teaching during 2011 to 14. Apart from his academic interests and responsibilities, he finds fascination and recreation in nature photography. With this brief introduction, I request Professor Amber Habib sir to deliver the lecture. Thank you, sir. Over to you, sir.
Thank you very much for the kind invitation to be part of these proceedings. Let me share my screen and let's get started.
Yeah, start.
Yeah. Okay, so hello everyone. Now, the topic for today's talk is Newton's method and fractals. Fractals are something that we hear a lot about, and there are very many pretty pictures of fractals, whether purely mathematical or their realizations in nature. One of the fascinating things about them is the way they can crop up out of some very simple processes that don't look very complicated, and you would expect that the outcomes would be straightforward, turn out not to be so. Now, even on this first slide, the title slide for this talk, I have put some of these pictures that we will in fact look at in today's talk, and we'll try to understand some aspects of how these pictures come to be and what are they showing, what is the mathematics behind them. Okay? Now, as I said, this is something we hear a lot about. As a mathematician, I had heard various things about fractals. I'd seen the pictures, but didn't really have occasion to do anything with them for a long time until they kind of cropped up on their own in a numerical analysis course that I was teaching. I just asked a question that seemed sort of very commonplace question, and I asked students to work on it. And the results were a bit surprising to me. And then I had to look into it more. And I then came to know that we had actually run into one of the starting points of the theory of fractals, one of the examples that is important there. And so that is sort of the nature of this subject. It just crops up on its own even when you are not looking for it. Okay. And sometimes it shows up in a way that is disguised, and without exposure to these things, you may not realize that you have come across a situation which has a fractal underlying it. And in one place today, we will see how that can also happen. Okay, so let me start with the question that started this for me long ago. Okay, and so one reason that I like this topic is that it's an excellent topic for teachers to use to get their undergraduate students interested in, say, a project or some experimentation of their own. Once you have understood the basics, it's very easy to do some programming and generate these pictures and explore the different aspects. And as you do that, you will find out both limitations of mathematics and programming, and that may take you to deeper questions. So the basic question that we will start is about finding roots of polynomial equation, right? And so, you start off in the usual straightforward manner. You take the simplest example first. You take a linear equation like this. It's easy to solve, provided, of course, that you know about negative numbers. But as long as you know negative numbers, you would not have any difficulty in solving this equation. So far, so good. Raise the degree by 1. It's a little more complicated now. Even though, humans knew how to deal with quadratic equations as long as about 4,000 years ago. In Egypt and Iraq, they were able to deal with them from a geometric understanding of areas of do them by knowing only real numbers. Okay. But things change when you go to cubic equations. From linear to quadratic is a jump, and from quadratic to cubic is an even more serious jump. As it turns out, there is a formula for the quadratic equation, there is similarly a formula for cubics, and it involves, as you would expect, cube roots and some combinations to solve the cubic. But the funny thing about is that you cannot make sense of this formula at all if you do not know complex numbers. Okay? Even when the cubic has real roots, all the roots are real, you still cannot solve that cubic without using complex numbers in between. And that's a very remarkable thing. If I remember correctly, while the formula was discovered by Italians in the 16th century, a bit later it was Lagrange who pointed out the inevitability of having to use complex numbers in this formula, that even when solutions were real, you still needed to work through complex numbers to find them. Yeah. But let's take a look at a simple cubic and see what the solutions look like. Okay. So here is a cubic equation that's not looking very complicated, and the cubic polynomial, I have plotted it. And you can see this is an example of a cubic which has 3 distinct real roots, right? Okay, there's some background noise. People can mute themselves. Okay, so all right, so take this cubic polynomial, and it has 3 real roots. And what we can do is, excuse me, somebody is talking in the background. Please mute yourself.
Or the organizers.
The organizers, you have a mute all option, right? Please use that. Or find who is talking and mute them, please. Okay, thank you. It's very difficult to control these things, I know. Okay, so take this cubic, and it has 3 roots. Now, the formula for solving a cubic is somewhat complicated. I don't want to show you the full formula, but suppose you opened some software like Mathematica and entered this equation into it, and you ask for the roots. This is what you would see in that, okay? So you see that there are 3 x values that are given, these complicated expressions, right? And they all involve actually some complex number. The I root 3s are present in different places. Okay. Now one can prove that if you were to expand the real and imaginary parts, then the imaginary parts would cancel and you would only get real things. But there is no way to that final real answer without going through this stage where you first see these complex expressions. Okay, so that's the complication here. But still, there is a formula, so that is good. In principle, you can find exact solutions for cubic equations. You can do the same for degree 4. Okay. But for degree 5 and beyond, as I'm sure you don't have this kind of formula. You don't have some analog of the quadratic formula for degree 5 and beyond. And it's not just that we have not been clever enough to find the formula. There just isn't one, and it has been proved that there isn't one. Okay, so where does that leave us? So that means that if you are faced with a polynomial of high degree, in general, you cannot hope to find the solutions exactly. You may be able to, with some luck and cleverness, but there is no general formula that will always do the job for you. And so as a general procedure, what you have to settle for is the finding of approximate solutions, okay, rather than exact solutions. And there are different ways in which you can generate approximate solutions of a polynomial equation. One of these was given by Newton and his teacher Raphson, in the 17th century. These are the years when they mentioned this method in different publications. And so what they said was that suppose you have a polynomial px and you are looking for a solution. And what you have initially is an approximate solution. So maybe you have a number a so that px is close to 0, but is not exactly 0. And you're thinking, okay, at least this is some estimate of the actual solution. And so the question is, can you improve this and get a better estimation out of this? So what Newton and Raphson said was that you should do the following. Take the now if a had been an actual root, it would have exactly divided, then x minus a would have exactly divided px. So the extent to which it fails to divide px could be a measure of how much this approximate solution is off, and it could give you a handle on how to improve it. So what you do is you divide px by x minus a. And so you now have written px as x minus a times another polynomial qx plus a constant. And if you plug x equal to a into this, then of course that c will turn out to be p of a, right? And so you get this expression px is equal to x minus a qx plus pa. Now suppose you had, look at an x which is actually a solution, right? Then p of x will become 0. And let's assume that we were lucky with our first a and that a was close to x, right? Well, if a was close to x, then q of x would be close to q of a. So let's, as an approximation, replace the q of x term with the q of a term, right? Since they are close to each other. So now instead of an equation, you have something which is an estimation that x minus a qa plus pa will be close to 0. And then you can solve this for x and get the expression x being a minus pa upon qa. Right? Now, of course, this will not exactly be x. The right-hand side will not exactly be x. What you're hoping for is that it will be close to x and that it will be better than a. Starting with a, you have this correction term minus pa upon qa, which is hopefully improving the answer. So that is the method that Newton and Raphson gave. Now, this is, of course, not the Newton-Raphson method that you learn in school and university, where, in fact, derivatives are involved. So that improvement is due to Simpson a little later. And Simpson noted that if you look at this first thing, right, a minus pa upon qa, and you look at this qa a little closer, and let us take this px equal x minus a qx plus c, differentiate both sides, and put in x equal to a. And if you do that, you discover that qa is the same thing as p prime a. Q is not the same thing as p prime, but qa turns out to be the same thing as P prime A. Okay, so therefore Simpson suggested, well, that is a formula you can apply to any function, right? You can, for any function f, if you're trying to solve fx equal to 0, and you have an approximate solution A, you can look at A minus fa upon f prime A, and you can hope that that is an improvement. Okay. All right, so this is the formula that we are taught in numerical analysis courses and sometimes in calculus courses. And let's take a closer look at some aspects of this process. Okay. Let's stick with our x cubed minus 3x plus 1, for which we saw that there are three, the graph looks like this. Clearly, there are three real roots. Now, what happens with the Newton method is that if your A was somewhere here, then taking A minus fa upon f prime A amounts to doing the following, that at starting with your A, you look at the corresponding point on the graph of the function, you find the tangent line, you follow the tangent line until it hits the x-axis, and that is your point A minus fa upon f prime A. Okay. And so this looks also intuitive, that if you were at a certain point on the graph and you wanted to move towards the root, what should you do? You should find the tangent line and you should move in that direction, because if the function is differentiable, the tangent line may be a decent approximation to the graph, may not deviate too much from the graph. And therefore, the place where the tangent line cuts the x-axis hopefully will be close to the place where the graph itself cuts the axis. And the closer this original point was to the x-axis, the better this idea would work. So there's an intuitive aspect also to this Newton-Raphson method. Okay. Okay. Now, suppose we want to make a general sort of approach out of the Newton-Raphson method, right? So what is the method? Start with a random point and keep applying this iteration A minus fa upon f prime A to create new points, and then apply again. Hope that you are moving towards the solution. So the first question, of course, is, if I start somewhere, is the guarantee that I will move towards the solution, that this process will actually improve the situation. Okay. All right. So that is one question. And the other question is, generally the polynomial will have many roots, right? And so you start at some point, even if you move to a root, which root are you going to move towards, right? So if you start with a first estimate for a root and you apply Newton-Raphson and you're lucky and it takes you towards a root, but there were several of them, which one is it taking you towards? And can you methodically figure out, these starting points will take me to the x1 root and these starting points will take me to the x2 root and so forth. Can you take the real line and figure out which points go to which root, right? And if you can do all this, then you have a general understanding of what the method is doing. Okay. All right, so these are two questions. And what kind of answers that we have to the first question? The answer is no, not every starting point will go towards a solution. Okay. And to the second, it is which can we identify? Well, you can for some of them, or maybe for many points, you can identify what will happen when you apply Newton-Raphson. But for certain points, and even for a significant number of points, it may actually be difficult to figure out what Newton-Raphson is going to do to them. Okay, and you may not be able to have a nice description of overall description of these points don't lead to a convergent iteration, these points do, and this is where you go. You may not have a neat response to these questions. And that is actually the good news. The fact that we don't have those simple, clean answers means that something interesting is happening that is worth exploring. Okay, just for the first thing of how the answer can be no. So this is actually the graph of the arctan function, and you're applying Newton-Raphson to it. And here are two examples of what can go wrong. If, for example, you start off now with Newton-Raphson in such situations, there is a theorem which guarantees that if you start close enough to the root, then you will actually end up there through Newton-Raphson. And things can go wrong if you happen to start a little away from the root, not close enough. And here, for instance, if you take this x1 and then you follow this tangent line, come to x2, you see that you've actually moved away from the origin. And if then you again at x2 take the tangent line and follow the tangent line, you come to this x3, you see that x3 is worse than x1 was, right? So things have become worse, and applying Newton-Raphson is actually taking you further and further away from the solution. It is not moving towards the solution. So there's one of the things that can go wrong. Okay. Another thing that can go wrong is that you actually don't really move. You start from a point, you follow the tangent line, you go again, and you end up at exactly your starting point again. Okay. This might, so Newton-Raphson may also do the following, that you start with a certain point, you apply Newton-Raphson a couple of times, you end up back there. And it may happen after 2 iterations or 3 iterations or 4 iterations. Okay, after some number of applications of Newton-Raphson, you may end up back at your starting point. Okay, so this is called cycling. Okay, so the first was what one would call divergence or blowing up, where you're moving away from the solutions. And here you simply basically stay stationary. You move through the same 2 points over and over again. Okay, so that's cycling. Okay. All right. So, but now let's return to, so just to be aware that things can go wrong, but now let's go back to the thing that we really wanted to study, x cubed minus 3x plus 1. Let's look at the graph, and certain things you can visually figure out as to what the Newton-Raphson method is going to do with x cubed minus 3x plus 1. For example, suppose I were to start, say around this 1.5, right? So you would come here and you would take the tangent line. And so you would move down here to 1 point something, say 1.2, move up, take the tangent line again. You see that you steadily move towards 1 if you follow Newton-Raphson like this, right? And similarly, if I were to start, say, somewhere here and then take the tangent, I would move into the greater than 1 region. And then after that, the whole thing would repeat. And so again, I would have convergence. Visually, one can figure out that if you take this place where there's a minimum and you work with points to the right of it, then Newton-Raphson will always, starting from there, will always take you to the root at 1. So in this whole interval, this point, this minimum incidentally is at 1 by root 3. So in this whole interval beyond 1 by root 3, all starting points will take you to 1. Similarly, all starting points to the left of -1 will take you to -1. And one can also figure out without too much trouble that all starting points between plus minus 1 by root 5 will take you to 0. But there is a little sort of small interval here and another small interval here where it's harder to figure out what's happening. And you can carry out explorations and you can figure out smaller intervals and say, okay, points here will go to 1, points here will go to -1, points here will go to 0. But you also find that the process never stops. You keep finding smaller and smaller intervals with differing behavior. So overall, in these two small intervals where I have put the question mark, you really don't have a clean, neat picture of what is happening, right? And that's actually in my own numerical course where I first encountered, by chance, this fractal behavior. I was asking students what happens in these various portions of the real line, and we found that depending on which exact point students took here, they gave completely different answers because points had different behavior. Okay. Okay. Now, what we are going to do to get more insight is that we are going to move from the domain of real numbers to the domain of complex numbers. One reason for that is visual. When you work with the real line, you're just working along the real line. If there are subsets and of the real line and there are many subsets, there's not much you can do by way of drawing to get better insights into what's going on. But if you work with complex numbers, you're working in the plane, shapes when they overlap and they do other things, visually you can get a better impression and you can immediately sort of perceive what's happening. So that is actually my main reason, but also you may know by now that many things which are obscure when you work only with real numbers gain clarity when you work instead, when you expand the number system that you are working with and shift to complex numbers. So that is also a reason for doing what I'm now going to do. Okay. All right, so let's instead of working with functions of real numbers or polynomials with real coefficients and real input variables, let's work with functions where the inputs and outputs are complex numbers. Okay. And so now let's say there's a function of complex numbers, and again you want to find where are the places where it becomes 0. You want to solve the equation pz equal to 0. You can define differentiation for complex functions exactly as you define it for real numbers. And based on that, you can create the same Newton's method and say that if I have an approximate solution Z0, then I'll improve it to a solution Z1, which will be Z0 minus PZ0 divided by P prime Z0. So the same Newton's method can be extended to the complex situation. And here we can ask again what's going on. The points which under Newton-Raphson take you to a certain route, we will call the basin of attraction for that route, right? The points which are attracted to it when we apply Newton-Raphson. Arthur Cayley was the first one to suggest that this is an interesting problem, that we should look at complex polynomials and to identify the roots and to see what Newton-Raphson does. We should look at the picture of the complex plane and see which starting points are ending up where. And he did it for quadratic equations. Okay. And this is what he found. I'll just show you one example, but the general picture is also pretty much the same. Let's just take a very simple example, z square minus 1 equal to 0. The roots are obvious, right? Plus and minus 1. And so if this is the complex plane and the origin is right in the center of this box, then the root minus 1 is over here at on the left edge, and the root plus 1 is over here on the right edge. And the Newton-Raphson method looks like this, right? This is your pz, zn square minus 1, and you are dividing by 2 zn, which is your p prime. You are subtracting from zn. You can simplify this and get half zn plus 1 upon zn. And one can figure out from this that if you do this repeatedly, then if you had started with a Z0 whose real part was positive, then you would always converge to plus 1. And if you started with one whose real part was negative, you would always converge to minus 1. Which it makes sense because the roots are kind of symmetric about the y-axis. So it kind of makes sense that everything to the right of the y-axis should go to plus 1 and everything to the left of the y-axis should go to minus 1. But then there is the y-axis itself. And you can see that if you were to take a starting point on the y-axis, then it would not converge to any root, because if Zn was purely imaginary, then 1 upon Zn would also be purely imaginary. And therefore this combination Zn plus 1 would also be purely imaginary. So points on the imaginary axis stay on the imaginary axis under the Newton-Raphson method and do not converge to either root. Okay, so that's a very simple sort of decomposition that we have of the complex plane. And for a general quadratic, it's basically the same, because by completing squares, you can essentially move into a z squared plus constant equal to 0 situation. Okay, so this is what Cayley did, except that, the notation for working with complex numbers and so on was not so nice in his time. So he had to do much more work in terms of explicitly writing down real and imaginary parts and the angles and the arguments of the complex number and so forth. It's much easier now for us. But then Cayley said, well, okay, so quadratics are done. What happens with cubics? And he was not able to get anywhere much with cubic equations. Okay. And he just leaves it as a comment that I have done quadratics, but I have not been able to do cubics, not been able to work out what happens with cubics when you apply Newton-Raphson. And this is something interesting for the next generation to look at. Now, why does this happen? Now that we are in a position to make nice drawings with the help of computers, we can understand what made it so difficult for Cayley. So again, let's take a simple cubic, not too complicated. Let's simply look at z cube minus 1 equal to 0. Okay, so z cube equal to 1, and so the roots are simply three numbers, right? Equally spaced on the unit circle, the three roots of unity. So we already know what the roots are. And so what would you expect, right? So if the quadratic picture was to hold, right? So if you have three cube roots, what you would expect is that the plane should then be divided into three parts. And the numbers in one part would converge to one root, and then in the second part to the second root, the third part to the third root. You might expect three rays at 120-degree angles, right? Cutting the complex plane into three congruent parts because of the symmetry. And each one of those corresponding to where you end up. Okay. Well, it's partly like that, but it's not quite like that. Let me show you how it actually looks. This is how it actually looks. Okay. So this very simple question has led to an amazing picture. Where are the roots? There is a root in the middle of this, on the right, in the middle of the right edge, right? That root is simply +1. And there is a root here, right? And there's a root in the red portion around here. So there are three cube roots of 1, which are symmetrically placed around the origin, which is right in the middle here. And you do have those three big regions of convergence for each one of them, but the meeting point is no longer simple like it was for the quadratic, right? It's not just a straight, simple line as the boundary. The meeting where you expected that, you instead see a much more complicated situation. You see these sort of teardrop shaped places, and then on top of them other, and then still smaller. And here is where interesting things happen. So for instance, you could ask, what's really happening, say, in this part with the big red teardrop shape? Let's take a closer look at that. And this is what it is. And you see that its own boundary is again, right, made out of teardrops, and then their boundaries again have teardrops, and their boundaries again have teardrops. And this just goes on forever. And so naturally, Kelly was not able to identify the basins of attraction for even a simple cubic like this one, right? Okay. So certain interesting things are happening here. One of them is, and one of the interesting facts around here is that once, because you said have some points so that if you move around them, you have points of the same type, right? Like all the blue points are all here in this region are all going to the root at 1. But suppose, you were to take a point like the origin, for which actually Newton-Raphson will not work. So what's special about it? What's special about it is that the blue, yellow, and red regions are all meeting there. And so what happens in this is that wherever there are, boundary points between the three blue colored regions, all three regions meet there. And the necessity of all three regions meeting there is what is creating this situation of more and more teardrops. Because no matter which teardrop you have gone to, when you look at the boundary, again, three things have to meet. Again, a fresh teardrop has to be created over there. So this is how this particular sort of fractal shape, with self-similarity, as you zoom in, you simply see the same pattern again, comes out of a very simple basic question and an extremely simple polynomial for whom we are trying to figure out how the Newton-Raphson method works. And then you can play, of course, with different polynomials, and you can create different pictures of this type. Again, I'm not going to complicate it much right now. Let's consider z cube minus z equals 0. So this factors as z into z square minus 1. So the roots are 0 and plus minus 1. So you have three collinear equally spaced roots. Again, if one were thinking naively, one would expect maybe one sort of strip in the middle for the 0 root, and then two big regions on each side for the plus and minus 1 roots, and some clean boundary between them. But it is that clean boundary that doesn't happen. This is what actually happens. Okay. Right. So we have the root 0 in the middle, and then 1 over here, minus 1 over here. The red points are ones which lead to convergence to -1, blue to 1, and yellow to 0. And you have this boundary, but again, this boundary is not, a clean, simple boundary. There are again these sort of cactus-like shapes, little cactus-like shapes on the boundary, and they're everywhere, right? Here are the bigger ones, but there are smaller ones and still smaller ones, and there is no escape from them. Let's zoom in a little bit. So I'm zooming into this red one, and again you see that on the same pattern is repeating on top of this red sort of cactus shape, right? Smaller cactuses on top. Actually, real cactuses sometimes also look a bit like this. Here's one, right? There's the main shape and then a smaller shape of the same type and then more on that. There's 3 levels, but your mathematical cactus, of course, never stops and the branching keeps happening forever, okay? And then by varying the location of the root, varying the degree of the polynomial, you can create more and more interesting and colorful patterns, fractal patterns. Now, one of the things that has happened in the example so far is that you're basically seeing, it looks like everything is either red or blue or yellow. Right? That is giving the impression that no matter where you end up with, you would end up at, no matter where you start, you would end up at one of the roots. If there are trouble points, then there maybe are a few of them scattered on these complicated edges somewhere. There may be a few points, but it looks like the general point is going to go to one of the roots. But that is not generally true. So just as a warning, for instance, if you were to take this particular cubic, and again, you would have 3 colored regions for the 3 roots, but there is also what I've plotted here as these black regions. And these black regions are regions where if you start here, then you end up not converging to any of the roots, okay? You end up simply, as you apply Newton-Raphson, you either keep jumping within one of these black regions or you end up jumping from one black region to another black region, but you never end up in one of the colored portions, which will take you to one of the roots. So there may be significant areas of the complex plane which are dead ends. If you start there, you will not move to a root. And here's a closer look at one of those, at this black region itself. Okay, and this very nice sort of almost this tiling kind of pattern all around. Okay, so now that's the general thing, just asking that if you start at a point, where will you go and will you end up at a root or not, which root? But we can ask more questions. In Professor Idisha's lecture yesterday, one was talking about orbits, and maybe you have recognized that really we are doing the same thing here, right? So what's happening is that there is the Newton-Raphson iteration, that's a certain function which is being applied over and over again. And that creates what's called an orbit, and we are interested in the long-term behavior of this orbit, and it could do different things. Potentially, it could, the terms could just get bigger and bigger, and it might shoot off towards infinity, or it might move towards some solution and settle down there, or maybe it might cycle through the same values over and over again, and potentially also maybe it just is sort of random and jumps all over the place without any clear pattern to what it is up to. Right? We can imagine different situations, and we should therefore look at whether these different situations really happen and whether we can study them, right? Whether we can identify what's going on. Okay. So here is one of the things. We have already seen that even in the real case, we already saw, right, that your orbit under Newton-Raphson might shoot off to infinity, and also that it might cycle. So that kind of behavior we have seen. It may also go to a solution. So this kind of behavior we saw even in the real case, and of course it will also happen again in the complex case because that includes the real case. What about chaotic behavior? Meaning, could there be movement which is hard to understand and looks random, right? Okay, so there are 2 aspects to this. One is a particular orbit. How does it behave as you move along it, and whether it behave in a regular way or a random looking way? And the other aspect is that, okay, you had a certain orbit when you started with a certain starting point, and what happens if you slightly change that starting point, right? What does that do to the rest of the orbit? Now, the fact that there are portions with very fine structure where the red, yellow, blue regions are very small and extremely mixed up with each other tells you that starting point there, if you perturb a little bit, the behavior of the orbit will completely change, right? Because in perturbing the starting point just a tiny bit, you might move from a blue region to a red region, right? Because they are so small and so mixed up. And then you, instead of going to 1, the orbit would go to -1. Okay. So that's one level of instability or chaos that could happen. And the other is what happens along an individual orbit. Well, let's see. Let's just even apply a Newton-Raphson to a simple quadratic, z square minus 1 equals 0. Remember that points on the imaginary line stay on the imaginary line. And for Zn, if I now take the imaginary part to be yn and I write it as Iyn, then the formula for Zn plus 1 gives me the following formula for yn plus 1 in terms of the previous yn. Half yn minus 1 upon yn. Right? Because Iyn plus 1 upon Iyn, so that gives you the minus sign. Okay. And you can, again, intuitively sense what would happen if you started with a point which was high up on the y-axis. Yn was large, then 1 upon yn would be small, ignore it. That means that essentially you would move from yn to yn upon 2, and then you would halve it again and so on. So roughly you would be halving the y coordinate for a while, but this would change as you approach the origin. And for example, if you ended up with yn, once yn becomes close to say 1, then 1 upon yn will also be close to 1, and the difference will be close to 0. And then once the difference is close to 0, 1 upon yn will be huge. So in the next step, right, so you will have been moving down, come close to 1, jump close to 0. And then the next thing you are kicked away, right, because of the 1 upon yn. So this, you have a behavior down, 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 and then sudden up. Let's look at a numerical example, right? So this is what happens. Suppose you started at yn equal to 10. So you were starting my iteration at 10 times I.
Conference attend avvadaniki edo chudandi.
So first you would come to about 5, then to about 2.5 and so on.
Online
come close to 0, 1, and then to 0, and then you would, magnitude would suddenly jump and you're way over here, you come down, and then again jump, and then come down. So you see, it's a little unpredictable kind of behavior that's happening. And when there are jumps, right, it's hard to say what will happen. There could be a medium jump, or there could be a really huge jump as well, depending on how close yn came to 0. Okay. Roughly, you can see that you can expect most numbers to be, say around 0, 1 kind of range, and relatively few above, because as soon as you go far, you are kicked back, right, to half of that. Okay, so now I'm going to show you the result of tracking this orbit through 10,000 steps. Okay, and then plotting, making a histogram of the different y values that one sees, and this is what you see. Things are concentrated around 0 and die out, but you do keep seeing quite large values. Okay, as you go, and this will extend. Okay, I just truncated it here. Okay. And that's interesting, right? I mean, it looks like one of our familiar things that we might see in a probability course. If you showed somebody this and said, I have some data and this is the histogram, what would they think? They would think that you have plotted some random process, maybe following the normal distribution or something similar to that. And out of that random process, repeated observations of a random process, you have created this histogram. But in fact, we have actually been tracking a deterministic rule. Okay, right? Yn, half of yn minus 1 upon yn, a very simple deterministic rule. And that is what has created this, right? And so that is kind of, that relates to something I said at the start, that one of the interesting things about fractals is that things that seem random, through fractals, one might hope to have a deterministic explanation of those data. Okay. Okay. All right. Now, we saw that you can have in Newton-Raphson that you can have two cycles, meaning you start at x1, go to x2, come back to x1, right? And so there's an example of such a two cycle from the same z square minus 1. So in fact, on the y-axis, there's a pair of points which just cycle between each other. Now, suppose you do this numerically, right? So you feed it into your program and you just keep applying Newton-Raphson over and over again. And so you keep seeing the repeated values and keep seeing the repeated values. And then suddenly, instantaneously, the whole thing breaks down. You go a little bit off, a little bit more off, and then completely off, right? Like this. What has happened? What has happened is that you were trying to oscillate between something like plus minus 1 by root 3. And so, of course, you had some decimal approximation to that in your program. And therefore, as you computed, there was always some rounding of error, and that was increasing tiny bit by tiny bit from stage to stage. And visually, it's not something that you would notice. You think you are just oscillating between the same 2 points. But at a certain stage, the round of errors became just enough to kick you away from the cycle and into one of the colored red and blue zones. Okay. Sorry, this is still imaginary. So it just kicks you away from the cycle. And once you're away from the cycle, you get returned to the chaotic behavior that we have already been seeing, right? And this is what happens if you were to start with a 2 cycle like this and just do it again over thousands of steps. Okay. If you may not be able to see this clearly, but there's a tiny part here which is you can just see, 2 thick sort of black bands, one above the other here for a little while. And that is this part and this part. And then things break down and then it's just haywire, completely random, right? Now, this sort of thing could be noise from some process. If you were to plot stock prices sometimes after normalization, this is the sort of pattern that you would see, right? So one sees this sort of pattern often enough in nature, and it's quite fascinating that it's coming out not genuinely out of randomness, but out of a deterministic process, which is very sensitive to perturbation. Okay. All right, so what kind of orbits and orbit behavior do we have, right? So what have we seen so far? One is that you can have cyclic orbits which repeatedly go over the same point. And in that, I could include even, the behavior where you simply stay at the same point all the time. That will happen if you start with a solution, then you will just stay there and won't move at all. Another thing that can happen is that you have an orbit which is not cyclic, but over time converges to a cyclic orbit. And again, the special case of converging, the case of converging to a solution is a special case of converging to a cyclic orbit. That's another thing that you could have. The third thing that we have seen that you could have is that you could have chaotic orbits, right? So we have seen already this very different kind of orbit behavior. Okay. And so if you slightly perturb the starting point, the perturbed orbit may stay close to the original one, or it may completely change. And so what's interesting naturally is where are the points which are so sensitive, so that if you perturb a little bit, then the orbit behavior will change. And these are called the Julia sets for this process. And these are those boundary points that we had seen before. And they form these nice patterns. Okay, so this is basically what I want to say about Newton-Raphson. I'll just say something a bit more general for a few minutes, and then we will stop, and I'll quickly show you some more pictures of fractals. Okay, so now this kind of iteration that we did with Newton-Raphson, you could do with any function, right? You could take any function phi and repeatedly apply it and ask what kind of orbits are created. Now, what are the simplest functions? If you take a linear function, not much happens. You just keep having linear changes. But if you take a quadratic function, then many interesting things happen. And let's look at that. And let's just look at z squared plus constant, things as simple as that, and ask what happens when we repeatedly iterate. Okay. So because we are short of time, I will simply show you the pictures that happen in this. I mean, there's a basic study you can do similar to what we did for Newton-Raphson. Okay. But here what happens is that two kinds of things can happen. A particular orbit either just stays bounded, and within that it may be chaotic or uh, cyclic or whatever, or convergent, or it may shoot off to infinity. Right? These are two kind of drastically different behaviors you can have. So if starting point takes you to infinity, we say it's part of the basin of infinity. So most of the complex plane will be this. And some starting points lead to bounded orbits. Okay. And that what the set of those points we call the filled Julia set, and the boundary of that we call the Julia set. Okay. For instance, if I just had c equals 0, z squared, right? If you start with a number whose mod is 1, you would just keep rotating around the circle because mod would stay 1. If you started with a number with mod less than 1, you would move to origin, start with a number with mod z more than 1, and you would have bigger and bigger magnitude, and your orbit would blow up. So these are the three behaviors. In this case, the circle is the Julia set. The whole disk that it contains is the filled Julia set, and everything outside the disk is the basin of infinity. Okay, now that's a simple picture because C was 0. Soon as C is non-zero, funny things happen. Here is what happens for z squared minus 1, right? It's a drastically more interesting picture. Okay, so things shaded black, that's the filled Julia set, the points leading to bounded orbits. The light gray is the basin of infinity. And the boundary, which are this that I've drawn here, this is the Julia set itself. Okay. Okay, let's see quickly, right? And so you can vary C and create all sorts of different Julia sets. And here are some examples. If you take negative C's, what you get. And here are some examples of what happens as you move along the imaginary axis. Okay. And you might see two kinds of behavior. One is that you see a single solid sort of chunk, right? Like here and here. And even here, I mean, it's one connected chunk, but here it's broken up. And here also, though you can't see it clearly, it's broken up, whereas here it's one connected strand, even though it's branching off, but it's one connected piece. So there are these kind of two extreme behaviors that happen. This is called the fundamental dichotomy. Okay, that Julia sets are either connected, meaning one solid chunk, like in these black portions, given any 2 points, you can connect them by a path, or totally disconnected, meaning there are no connected pieces at all. Take any 2 points, no matter how close in this set, and you will fail to connect them by a path that lies within the set. So here, like in this thing, which looks like, some Diwali sort of cracker thing, you have these spiral shapes. If you zoom in, each part simply looks like another spiral shape. Okay. So you have these different pictures that can happen, and here are more pictures that can come up out of this very simple process. Okay. And then the famous object that's created out of this is called the Mandelbrot set. In the complex plane, you look at z squared. For each C, you look at whether z squared plus C leads to a connected Julia set or a disconnected one. And the ones which lead to connected are shaded black here. And that leads to yet another famous fractal shape called the Mandelbrot set. So I'll stop here. Just let me skim through these pictures. And you can see what are the various fascinating shapes that we come up with through these explorations. Here's some news items. Field medal work has come out of explorations starting like this. And Kurt McMullen is a famous instance of that. And this kind of patterns, I've drawn it by, shown you pictures. It can also have patterns can be found everywhere. Fractal patterns can be found with numbers as well. Ken Ono did some famous work recently, very related some of Ramanujan's ideas to fractals. Okay. There are many nice books. Here are some of them that you can use. Some will tell you about fractals in nature, and some will give you the mathematical background. These are all very nicely written books that can be read from the undergraduate level onwards with different amounts of mathematics. There are also nice papers and websites that you can find which will talk about some of these things. Okay, and for instance, go to these websites and you'll actually find software where you can play with the equations and put in your own parameters and see what kind of fractals are created and do your own explorations into them. Okay. All right, so let me stop here. I see that I have already exceeded my time. So if there are any questions, I'll be happy to take.
Sir, thank you very much for your nice, informative lecture. Starting with the Newton-Raphson method, which is numerical method, and connecting with fractals and chaos. Thank you so much.
Welcome. My pleasure.
It is difficult to visualize, I think.
But it is great fun once you have things like Mathematica, MATLAB, and so on. By the way, I should say, while these are paid software, but Mathematica, for instance, has an online version that one can use for free. And while it has some restrictions, but all the pictures that I was showing today, like these are all Mathematica generated using the free online version. So while there are restrictions, but for basic exploration, doesn't really matter. And there's a lot that you can learn by playing around there. And some of the papers that I have put here, and if you, like these, will show you some of the Mathematica code that you can use to get started and then do your own explorations later.
Please share them on my email, sir.
I'll send you my PPT and you can share that with your faculty.
Slides also.
Yeah, absolutely.
Thank you, sir, for an informative session on Newton's method and practice. Now I call upon Sunita to propose formal vote of thanks.
Thank you, Shweta. It is my pleasant privilege to propose a vote of thanks on behalf of Department of Mathematics and Statistics of this esteemed institution. At the outset, I thank Professor Amber Habib, sir, today's resource person, for accepting our invitation and delivering such a wonderful lecture on Newton's method and fractals. Sir, we are highly impressed by the simplicity of your lecture, especially roots of polynomials, that linear, quadratic, and cubic polynomials, sir. How to apply Newton's method to cubic polynomials to get the approximate solution and complex solution of a polynomial equation, etc. I profusely thank you, sir. I would also thank the management, especially Professor Sudarshan Reddy, sir, Secretary cum Correspondent of our college, for permitting us to conduct International E-Symposium on Modern Mathematics. I sincerely thank our beloved principal, Dr. Achita Devi ma'am, for her support and guidance in arranging the program. I extend my sincere thanks to Coordinator and Head, Department of Mathematics and Statistics, Shweta Srivastava, for coming up with an idea to conduct 1 week International E-Symposium on Modern Mathematics. I also thank all the participants for their sincere participation. Last but not the least, I thank our faculty members for their efforts in making the program a success. Thank you.
Hello.
Hello.
Hello, good afternoon, sir.
Good afternoon. Am I audible?
Yeah, you are audible. It's raining here, so we are having a little technical difficulty. That's
Oh,
all.
no problem. No problem. Absolutely. No
That's all.
problem.
Simple adjustment.
No problem. I know. I was only worried that the trouble
It's
is
raining
my side,
hard,
not the
but
issue.
the heat of Hyderabad. Just a couple of minutes, okay? We'll soon be
Yeah.
with you. Just a couple of minutes.
No, no problem. Oh, no. Take your time. Take your time. I have no problem with it. Yeah.
Shweta.
Good afternoon, Arvind, sir. Good afternoon, Arvind, sir.
Good afternoon. Yes.
Hear me, sir?
Yeah. Good afternoon. Yeah, I am able to hear you. Yeah. I hope you are able to hear me without
Okay,
any
sir.
difficulty. Thank you.
Yes, sir. We can hear you, sir. Sorry for the inconvenience, sir.
Oh, not at all. Not at all. There are things beyond
Now we will
understand
begin
very
our
well.
next.
Yeah.
Yes, sir. We'll begin our next session by Professor Arvind CS, sir, on the work of Mariam Zahani. Now I call upon Monica to introduce today's resource person.
Good afternoon, everyone. I'm Monica. Ma'am,
Thank
can
you.
you hear my voice?
Oh, yes.
Good afternoon, sir. Yes. I'm Monica, Assistant Professor, Department of Mathematics and Statistics. It's my privilege to propose today's speaker, Professor C.S. Aravinda, sir, TFIR Center for Applicable Mathematics, Chikamasandra, Bangalore. Sir completed PhD from University of Bombay and Tata Institute of Fundamental Research. Sir interested in his research areas like Riemann geometry, ergodic theory, and topology. Sir visited different professional fields like mathematics group, ICTP, Italy as a mathematician, research associate at Indian Statistical Institute, Bangalore, and also reader. Sir have been a faculty member at the TFIR Center for Applicable Mathematics in Bangalore since 2007. Sir has many academic services as external reference at IIT Kanpur, reviewer and editorial member. Sir has a lot of teaching experience at different organizations at ISI, CMI, and TFIR. Sir published many research articles at national and international level and also published many books. Sir hobbies are mathematical outreach through expository and public talks and editing in English in Canada, translating, reading English, Canada, Sanskrit literature, trekking and listening to music. Thank you, sir. With this, I conclude and now I call C.S. Aravinda, sir, to take over the session.
Yeah, thank you. Thank you very much for your very kind introduction. So I think I should start by sharing my screen, I suppose. I could have actually done it while we're talking. So let me try. Host disabled participant screen. Maybe, yeah, I think I need to be enabled to share my screen. Monica, am I audible?
Sir, for 2 minutes, sir. We'll just
share. I'm trying to share my screen.
Sir, just wait for 2 minutes.
It says, oh, no problem, no problem.
I just shared you. You can share the screen, sir.
Okay. Thank you. Sorry, it went right to the last of the. Oops. Just give me a second. It went to the last screen first, unfortunately. Okay. Is my screen visible?
Yes, sir.
Am I audible and is my screen visible?
Yes, sir.
It's working fine. Can I start?
Yes, sir. You can start, sir.
Okay. Yeah. Thank you very much. Thank you very much. Okay. So maybe what I'll do is I'll just hold on a second. I don't know what's happening. Something went wrong. Yeah, I'm sharing my screen. Just hold on a second. I think there's something going wrong somewhere, or I'll just stop the video and I'll just proceed with this if it's okay with you, or maybe I'll just keep it on. Okay. All right. Yeah. Okay. Are things so Sunita, am I audible and is my screen visible?
Yes, sir. Yes, sir.
Okay. So faulty looks like, but if you say I can start, I will start. I'm ready to start. Oh, can I start?
Yes, sir, you can start.
Okay. Yeah. Yeah. Thank you very much. I understand, these days, getting to grips with technology is not always very easy, and lecturing from one place and another place where there's heavy rains and so on. I understand the difficulty. So let's not be deterred by all these difficulties. And I'm extremely happy to be talking about the work of Mariam Zahani. So without much introduction, let me just quickly get to the point. So I have put on my next screen in case there could be a little delay, and I think because of the unstable connection, sometimes the screen may show up a little later. If any such thing happens, please alert me. Please do not hesitate to disturb me at all. Okay. So this is the first slide. As all of us know, Mariam Zahani shot into fame, of course, with her work earlier. But I think she came to be known to the world when she won the Fields Medal at ICM, International Congress of Mathematicians, in 2014, and she was the first on several counts. And for her outstanding works on the dynamics and geometry of Riemann surfaces and their moduli spaces. So let me quickly run through. I hear that this particular international conference is in celebration of Mariam Zahani, the mathematician and the person. So let me just quickly run through the biographical sketch. Many of you may definitely know, but let me still go through it. Mariam Zahani was born on 12th May 1977 in Tehran, in Iran. She went to high school in Tehran at Farzaneghan National Organization for Development of Exceptional Talents. She won gold medals at the Indian International Mathematical Olympiad in 1994 in Hong Kong and at the IMO in 1995 in Toronto, where she was the first Iranian student to finish with a perfect score. So she obtained her BSc in mathematics in 1999 from Sharif University of Technology in Tehran. She went to the United States for graduate studies, earning a PhD from Harvard University in 2004. Yes, thank you. Yes, okay. So she went to United States for graduate studies. She earned a PhD from Harvard University in 2004, where she worked under supervision of Fields medalist Curtis McMullen Actually, I wasn't there for the entire talk of Amber, but at least I was there for the last, towards the last bit when he actually happened to mention the work of Kurt Macmillan. So I think it's in a sense, this talk, which is a continuation, seems like it's a continuation of Amber's talk. Okay, anyway, so she worked with, Mariam Zahani worked with Curtis Macmillan. And okay, she became a professor at Stanford University in 2008, and she was married to Jan Vondrak, a Czech theoretical computer scientist and applied mathematician, in the same year, and they had a daughter by name Anahita. Mariam was an invited speaker at the ICM 2010 in Hyderabad, so she has been to India. And she was awarded the Fields Medal at the next ICM in 2014 in Korea, and she was the first on several counts, first woman, first Iranian woman, everything. She was really, she really kind of, I think, heralded a very new era, you can say, in the ICM and the Fields Medal. She was diagnosed with breast cancer actually even a little earlier in 2013, and it unfortunately later spread to bones and liver, and she had to succumb to it, unfortunately, at the age of 40, barely at the age of 40, on 14 July 2017, leaving the whole world in sorrow and everything, actually. Yeah. So a brilliant life tragically cut short before it fully blossomed. The poignant story is succinctly captured in the 2020 documentary film Secrets of the Surface, The Mathematical Vision of Mariam Zahani by George Ciceri. I think this movie really, I think it, conveyed the power and inspiration of Mirza Khani's work, and of course many of us are celebrating even today. So that's Mirza Khani's life, brief life, really brief sketch of a very brief life, unfortunately. So now let me quickly overview a work of Mirza Khani's work. In her early work, she discovered a formula which expressed the Weil-Peterson volume of the modular space. I will elaborate a little bit on many of these things as I go on, but now it's a quick snapshot of her work. Okay. What are called border Riemann surfaces with a given genus and fixed boundary lengths as a polynomial in the lengths of boundary components. So this led her early work led her to obtain a new formula for the formula conjectured by Ed Witten and proved by Maxim Kontsevich, both of them Fields medalists actually, on the intersection numbers of tautological classes in the modular space. Her subsequent work focused on Teichmüller dynamics of the modular space, and she proved the long-standing conjecture that Thurston's earthquake flow on modular space is ergodic. And Thurston is again another Fields medalist. In 2014, with Alex Eskin and Amir Mohammadi, she showed that complex geodesics and their closures on in modular space are regular rather than irregular or fractal. Why we mention regular rather than irregular or fractal is because I'll show it in a slide a little later. Because in a rank 1 case, you can have closures, you can have closed geodesics which are fractal, whereas in this particular case, in higher rank, the regular. That's anyway. I'll touch upon it very briefly later. So as you can see, it encompasses a spectrum of areas. So let's now look at the basic setting for most of Mirza Khani's work. Okay, so let me start, since it's for the postdocs and teachers and students. So let me see, let me try to convey a little flavor of Mirza Khani's work. So let me start looking at the basic setting for most of Mirza Khani's work. Some of the words that I mentioned, I may be able to kind of elaborate a little bit on many of them. So a landmark theorem from about the late 19th century is the classification theorem of closed orientable surfaces. Closed orientable surfaces are sphere, torus, and so on. So it says, the theorem, classification theorem says that a closed orientable surface is necessarily homeomorphic to either a sphere or to a connected sum of tori. So let me just show by some pictures. The first one is a sphere, as you know, second torus, double torus, triple torus, and so on. As many holes as you can get. Of these, Zahani's work concerns the surfaces from the double torus onwards, namely from this one onwards, from this onwards, what are called surfaces of higher genus. Genus is simply, you could take it as a number of holes. So for instance, the sphere will be genus 0, the torus will be genus 1, the double torus will be genus 2, and so on. Number of holes. Okay, a surface of genus bigger than 2, it actually forms a common ground for several interesting structures. I'll try to describe some of them. You can say a treasure house, so to speak. It's a common ground for several different approaches, several different aspects, and so on. And that naturally leads to a variety of further interesting subjects which have surprising connections with seemingly disparate fields. So, and Zahani's work precisely brings out this fascinating interplay. To begin with, and actually when I quickly overviewed her work itself, already gave you how could one, cover such a wide spectrum. That's also because of the common ground in which she worked, is surface of higher genus, such a rich, fertile field to work, so to speak. So to begin with, let us recall that the most natural geometric structure on surface of higher genus bigger than 2, is what is called the hyperbolic structure. Hyperbolic structure means it carries a certain metric, a Riemannian metric, with Gaussian curvatures constant equal to -1. Okay. That's the reason why she looked at genus B equal to 2. I'll be able to convey why, some of these things, little flavor of it as we go on. So a surface of higher genus admits not just one hyperbolic metric, actually. It admits a whole family, what's called a Teichmüller space of hyperbolic metrics. To understand what we mean by that, let's step back for a second, okay, and look at the case of standard flat torus. So I mentioned torus. So what do I mean by flat torus? So you have seen torus. What is a flat torus? A flat torus is one where you visualize the torus constructed in this fashion. Namely, you look at the Euclidean plane, and you look at the square tiling, okay? And you know that the translations in the x direction, the y directions are isometries of the Euclidean plane. So now you take a group of translations, what's called z cross z, translating by integer amounts on the right side, and in the x direction, and translating by integer amount in the y direction, and take the group generated by that. So it's called z cross z. And if you take the quotient topological space of the Euclidean plane with respect to this action of z2, what you will see, I have described in pictures, is that you will get this square. And then because of the integer amount identification, these two sides have to be identified, and you will get this torus. Okay. Now, this is called a covering space of this torus, and you can, since we have quotiented by local isometries, the metric of Euclidean metric carries over, induces a Euclidean metric on the torus. So that is why it is called flat torus. Flat here means curvature 0. We know that the Euclidean plane has Gaussian curvature 0. If you do not know, it's intuitively very clear that the Euclidean plane has curvature 0. And so that is induced into this construction of the torus. Okay. So we are looking at the torus via this construction of Euclidean plane quotiented by the action of z cross z. And that is the flat torus. The torus that we normally visualize in three-dimensional space is not constructed like that. As we see it in three-dimensional space, it has curvatures of different signs as well. Okay, it has curvatures positive here in the outer rim, in the inner rim it has negative curvature. So naturally, it has on the rim it has 0 curvature, and that is not the metric on the torus that we are looking at. We are looking at the metric on the torus as constructed out of this construction, made out of this construction as a quotient space of the Euclidean plane by the action of isometries by z cross z. This is one metric. Interestingly, it is not the only flat torus, in the sense that you can also think of torus Euclidean plane you tessellate by parallelograms. So now you can see parallelograms means you can take different angles and lengths also very different. You can normalize the volume to 1, okay, And you can take the quotient space. Again, translations, same action, same meaning, action, you can define an appropriate action of Z cross Z. And so that the quotient space is a torus constructed out of this. So this flat metric on the torus is different from the one I mentioned in my previous picture, because here it is all perpendicular angles and here it's a very different thing. So you can normalize the volume to be 1, but you can get a whole family of metrics actually. So in fact, what is called a Teichmüller space T of flat tori with volumes normalized to constant 1. And that is the quotient space of flat metrics on the two torus. So yeah, Teichmüller space. So first of all, you have flat a whole family of flat metrics on the torus. And what is called the Teichmüller space is to look at the family of all flat metrics and you quotient by what are called diffeomorphisms actually. Okay, diffeomorphisms, group of all smooth diffeomorphisms on the torus, which are homotopic to identity. So on that's a sort of more handleable space. It's called a Teichmüller space. Okay, basically you want to understand the geometry up to diffeomorphism. So if you want to say up to diffeomorphism, you just quotient it out by the diffeomorphism group, of the identity, connected component of the identity. That's what diff 0 here. 0 means you're taking the diffeomorphism group and then take the connected component identity. Okay, homotopic identity. So anyway, so that's what a Teichmüller space is. At least you definitely know that on the torus, this is the case. So in fact, what does a Teichmüller space look like? It looks like a more familiar space. You can actually identify this Teichmüller space of a flat two tori with volume normalized to 1 by this group SL2R, which is all familiar to us, group of 2 by 2 matrices. You can take them to be determinant 1 and so that's SL2R, and you quotient out by SO2, group of rotations of the Euclidean plane, oriented rotations. So this is, you can identify the Teichmüller space of flat matrix with this space. So when you want to study Teichmüller space, you essentially look at this and the action and so on. So that's how you exploit the rich structure of the Teichmüller space. There's a typo here, it should be Teichmüller. Okay, so in a similar fashion, so we understand, at least you know what the Teichmüller space of the torus looks like. So how does the Teichmüller space of higher genus look like? So how do you study them actually? So to study the higher genus surfaces, let's say two double torus here and the torus with triple torus 3 holes. So you can actually construct, you can realize the double torus actually is constructed out of a octagon, 8-sided polygon with an appropriate pair identification. This A with this A, this B with this B, and so on. If you identify them, I have this diagram tells you that if you take this double torus, cut along this and spread out, you'll get an octagon like this. And a triple torus, I mean that is a 3-hole torus. If you cut along these appropriate curves, you get what's called a 12-sided polygon. So in a sense, you try to understand these higher genus surfaces by some familiar objects like this actually, like you understood the torus by square with certain identification, or a parallelogram with an appropriate identification. You try to understand these with octagons, 12 guns, and so on with appropriate identification. So it's not hard to see that one cannot tile the Euclidean plane. So for the understanding the torus, we tiled the Euclidean plane by parallelograms, right? But now in this higher genus surface, in fact, in the double torus itself, you have octagon. And you know that you cannot tile a Euclidean plane by octagons, regular octagons. In fact, more sides than 6, you cannot. 6 is the ultimate, as you know, hexagonal tiling is ultimate, among all polygons which tile the Euclidean plane. So what do? So we look for not the Euclidean plane, we get out of the realm of the Euclidean plane. We move to what's called the non-Euclidean or the hyperbolic plane. And remarkable hyperbolic plane, you can actually tessellate the hyperbolic even side hyperbolic polygon. So I'm trying to indicate diagram here, you don't look at a regular like the Euclidean octagon. The way you look at it is you look at it as this polygon, octagon like this. Okay, it's a hyperbolic octagon. And then these identifications, groups generated by these identifications give you, with a certain relation, give you a group of isometries. And again, like the way you quotiented the Euclidean plane by the appropriate group of isometries, namely Z cross Z, you realize the torus. You can similarly realize, you look at a certain appropriate group of isometries, the actually discrete group of isometries of the hyperbolic plane, you get the double torus. And by appropriate identification of the size. It's any this thing, 3-hole torus is a 12 gun and so on. So it's always an even-sided polygon, and you have appropriate pairs of sides. And the beauty is with the hyperbolic plane is the possibility is infinite, in the sense that you take a million-sided polygon, you can tessellate hyperbolic plane by million-sided polygon, so that you get an appropriate torus of that kind of genus actually. So it's as you can see, it's a fascinating field which opens up a lot of possibilities to study higher genus surfaces. The reason why hyperbolic metrics, so why are we interested in hyperbolic metrics? Not only because you can tessellate the hyperbolic plane with so many, any even-sided polygon, as I said. Why are hyperbolic metrics most natural ones on surfaces of genus bigger than 2? Okay. The reason is that there is another landmark theorem called the Gauss-1 Theorem, and I'll tell you a polyhedral of the Gauss-1 Theorem, which tells you that surfaces of higher genus, the most natural metric is the hyperbolic metric, namely metric of constant curvature, negative curvature -1. The reason why it's the most natural is because you take a surface of higher genus or any surface and look at what is called the total curvature, which means you look at the curvature at each point, integrate them over the surface, and you get a certain number. And so I'm trying to show, give you an idea. So if you integrate the Gaussian curvature over a sphere, you get a positive number. If you integrate the curvature, Gaussian curvature over a torus, you get 0. If you integrate the Gaussian curvature over a surface of higher genus, you will always get a negative number. Total curvature is negative. Because the total curvature is negative, the hyperbolic metrics on surfaces of higher genus, the natural ones, are hyperbolic metrics. So let's see why. What is total curvature? Instead of defining or going over the definition of Gaussian curvature, I look at what's called a polyhedral version of that. Okay, so I'll think of curvature as angle around a point in this polyhedral, representations. Angle around a point, for instance, Euclidean plane, the property is that angle around a point is 360. Okay, so you can roughly take angle around a point. If it is 360, you can roughly take that the point, meaning the curvature, Gaussian curvature at that point is 0. Okay, if the angle around a point is not 360, if it is more than 360, then it is negative curvature. If it is less than 360, it is positive curvature. You can take it that way. Okay, so if it was a cube without a hole, only points where the sum of angles around 360 are these corners, edges. So you know that, let me take this top left edge. The angle around that point is 90 plus 90 plus 90, 270. So 360 minus 270 is 90 degrees. Okay, so that's called the defect. Okay, 360 minus the sum of the angles is what is called the defect. So there is a defect there. So there is such a defect at 8 of these corners, 4 top and 4 below, for a total cube. I mean something cube, outer surface of a sphere. So there, naturally, it's all positive. 8 times 90 is 2 pi. I mean 4 pi. So you get that that's positive. So for a torus, namely, torus can be topologically thought, topology are told that you can, stretch and so on. You can do that. Topologically, you can deform a torus into this particular box with a hole like this. Okay. Okay, and there are 8 of those places, which is why we added up to 4 pi. And now there are these points, interesting points, these corners. Okay, am I audible? Are you all with me? Are you all with me?
Yes.
Hello, we can hear you.
Thank you so much. Yeah, please, as I said,
Power went off, so they're trying other generator things. But on laptops, there is power, battery is there,
Okay.
so it's going on.
Okay, thanks. No, I since there was silence, I was just wondering if I didn't want to.
Something suddenly went off, power went off.
Oh, I see. Okay, because I.
Hello? Hello?
Proceed. Hello, can I proceed?
Yeah, please proceed.
Can I proceed?
Yeah,
Okay,
please
good.
proceed.
Okay, so thank you, Ma. Yeah. So there are these places, these corners. Now, when you look at the angle around this point, it's not very hard. In high school, anyone can tell you that the angle around this point is, this is 90, 90, 90, 270 already, and then another 90 here inside 360, and then another 360 here. I mean, another 90 here. So 360 minus 450. So the defect here is actually minus 90 at this point, right? 360 minus the sum of the angle around this point. And there are 8 such points. Okay, so minus 90 at 8 points. So these places plus 90 at 8, minus 90 cancel out each other, and with the sum of the defects is 0, as you can see. So that's what I have stated here. Some of the defects at the corners, the points around which the angles are not equal to 2 pi degrees or 360 degrees, add up to 0 here for this. And for this, you basically have increased only the number of these inner corners like this, right? Outer corners are just only 8. So there's no difference there. And this already has cancelled the positive defects and introduced some more negative defects. Because of that, the sum of the defects at corners, only points where the sum of the angle around the point is not 360, they add up to minus 4 pi, a negative number. And naturally, if you go to a kind of a picture like this with 3 of these holes, so you get minus 8 pi. So you increase the number of holes, you get more and more negative. Okay, so the total, this thing, what's called the defect, sum of defects is negative. And actually there is an interpretation of Gaussian curvature as an infinitesimal defect. So instead of taking it to be such a nicely polished bookshelf, you can actually give polyhedral approximations of tori, finer and finer triangles, which almost look like the torus. And then the sum of the defects will be invariant. So they're 0. So that's a nice result that you can prove in high school itself. So because of the fact that higher genus surface, the total curvature is negative, the hyperbolic metrics, namely the metrics with constant curvature -1, are the most natural metrics on those surfaces. Whereas for torus, it is 0, which is why we called it, flat tori was the the curvature 0 metric on the torus was the more natural metric, not the one we visualize torus as embedded in 3-dimensional space, which has all curvatures. But even then, the total curvature, namely if you integrate the curvature at various points, even with the metric on the torus, induced from 3 space as an embedded, torus in 3-dimensional space, integral of the curvature will again be 0. Actually, yeah, that also is something not very difficult to visualize. Okay, so I suppose I have sort of made it clear why one is looking at the higher genus surfaces, and I suppose I have made it clear why the hyperbolic metric is a natural metric on that. And very similar to how we looked at the Teichmuller space of flat metrics on the torus. So you have a whole infinite family, a continuous infinite family of, in fact, a homogeneous infinite family of hyperbolic metrics. You can fix curvature -1 and fix a certain volume. There's a whole family of such metrics. And one studies what is called Teichmuller space. Okay. So one go about studying a Teichmuller space of hyperbolic metrics on surfaces of higher genus. Let me try to give a little idea. Okay. The idea is the following. So you take a surface of higher genus, you use what is called pair of pants decomposition. The reason why it's called pair of pants is because you decompose a given higher genus surface into pieces which look like this on the left side, a pair of pants. Okay. Okay. So how do you get these pieces? So suppose I look at a two-hole torus, right? It's a double torus, and I cut along these circles. If I cut along these circles, 3 circles, I get these 2 pieces. You can easily imagine that topologically, the top and the bottom are both pair of pants. So you take a 2 torus, cut along 3 simple closed curves, they don't intersect, this simple closed curve, and you get what called pants. Okay, so I write it cleverly, or at least prophetically as 3. I'll write it as 3 into 2 minus 3. 2 into 2 minus 2 is the number of pair of pants, and you cut along this number. The reason why I put it into 2 is basically because it's a 2-hole torus. I want the 2 to come somewhere. The 2 that's coming here indicates the torus. And you will see in the next one, when you take a 3-hole torus, you cut along how many? 6 simple closed curves. 1 here, 2 here, 3 here, 4, 5, 6. You cut along 6 simple closed curves, and you get 4 pairs of pants. So first pair of pants I have put it here. The second one is here, this one, and the third one is this one, and the fourth one is this one here. So you get 4 pairs of pants. So it's just a simple reduction, you can say. You keep including, you get, if you take a torus of genus G, meaning G number of holes, if you cut it along 3G minus 3 simple closed curves, you get 2G minus 2 pairs of pants. So it's very simple arithmetic. Okay. Now, when you cut along this, so you have 6G minus 6 parameters. Why do I get 6G minus 6 parameters? So 3G minus 3 positive real numbers called the lengths actually. Lengths. It's somewhat, when you remember the torus, the angle was one thing and the length was one thing. To get, let's say, a torus of volume 1, you could actually take it as a quotiented by square or by a rectangle, let's say, whose length is 2 and breadth is half. Okay. So you can vary the lengths and vary the, get this. And so the 6 parameters, namely the lengths and the twist, what is called the twist factor. You can just, twist factor is very similar to you got the parallelogram from a square by an angle, rotating by an angle. Okay, it's very similar to that. So you have 6G minus 6 parameters, which are 3G minus 3 positive real numbers. Angle is positive all the time, so it's positive real number. And the length is positive, and the angle, of course, you can go from, certain interval, open interval, you can say. Okay. Nevertheless, you get what the lengths and the twists. Okay, I'm not going to great detail actually. If it was an offline lecture, you could show some construction, actually show this, but it's perfectly fine. Let's do with an online lecture like this. So these parameters are called Fenchel-Nielsen coordinates. So which means given a G torus of G holes, you have these many coordinates for a point on the Teichmann hyperbolic matrix. Okay. So a Teichmüller space, the dimension of the Teichmüller space Tg of a Teichmüller space of hyperbolic matrix on a torus of G, genus G, is 6G minus 6. It's a 6G minus 6 dimensional space. And what is called the moduli space is different from the Teichmüller space. Moduli space is the quotient space of the Teichmüller space quotiented by a certain group. Okay, this group is called the group of all isotopy classes of homeomorphisms. And I'll not go into the any definition of that. I think these things you can actually find out, and more than that, it sits outside the purview of this non-technical talk. So isotopy class of homeomorphisms you look at, and this quotient space is called the mapping class group. Okay, and not the quotient space. This group is called the mapping class group, and the quotient space is called the moduli space. And that also, since it's a group mapping class group, it's again group. The modular space is the dimension is 6G minus 6. Okay. Now the 6G minus 6T parameters that I mentioned, the length and the twist factors, Li and Ti. Okay, it's somewhat like if you look at the flat torus, again, you can look at the lengths of sides and the angle. Okay, so that kind of, you can keep that picture in mind. So you have 6G minus 6, 3G minus 3 Lis and 3G minus 3 tau Is. These two parameters, totally 6G minus 6 parameters. And these parameters actually give another interesting structure. Apart from so far we have looked at what's called the Riemannian structure on the moduli space and the Teichmüller space. Now, on the moduli space, you get another structure called the symplectic structure. So this symplectic structure, it comes from essentially the symplectic 2 form. 2 form is actually, it's for those who are not familiar with this. So you look at coordinates and you look at the exterior derivative of this Li and dTi. So they are 1 forms. So it's a wedge of 2 1 forms. So they get 2 form. And you sum over all these 3G minus 3 of these Li and Ti pairs. Okay. So you get a certain 2 form. And that form is a symplectic form that gives another structure on this. So now you understand why I said it's a common ground of investigation for several interdisciplinary aspects on the moduli space. So now it's a 2 form. And if you raise it to the power 3G minus 3, you get what's called a normal form, top degree form. Namely, 2 form raised to 3G minus 3 will give you a 6G minus 6 form. And that's a top, what's called a volume form. Okay. And interestingly, looking at this way also in a natural way, I'm also kind of, going over some of these aspects very quickly. So you had a Riemannian manifold structure, a simple structure, and in a natural way, the modular space also has a structure of a complex orbifold. Okay, complex orbifold. It's, certain points may have be non-smooth. So the complex dimension would be 3G minus 3. Okay, so it has several different structures, and Zahani's work makes essential use of these structures and the interplay between them on the modular space. Okay, so she really kind of exploited the interplay of all these rich different structures, several different structures. Okay, so now let me just state a few of her remarkable results. Okay, what did she prove using all this rich interplay? One of my favorite is the following. Gregory Margulis, another Fields medalist. So it's a tons of Fields medalists in American language, you can say in this talk. Margulis, Fields medalist, had shown closed geodesics of utmost length. You fix a number L and you got the number of closed geodesics whose length is utmost L. Okay, and that number he had shown it grows exponentially with L. Namely, exponentially mean it is asymptotic to this particular number e to the power L divided by L, which means it's somewhat like a constant times e to the power L by L. Okay, for large enough L. That's what he had shown. So when he considered closed geodesics of length utmost L, you could actually, you don't really look at simple closed geodesics. Namely, you're allowed to, the geodesic is allowed to intersect itself. Okay. But since Mariam Zahani was working with this pair of pants decomposition and so on, cutting along simple closed curves, closed geodesics in particular, she was looking at the simple closed geodesics. Namely, among closed geodesics of length at most, she was only looking at that number of simple closed geodesics actually grows. I mean, I'll tell you how it this thing goes actually linearly, and that particular sorry, I kind of in my excitement I said something more than what I have not shown in the slide. So what I wanted to say is Margulis theorem is known as the prime number theorem for geodesic because it has a resemblance to prime number theorem in number theory. You know that. So Mirza Khani looked at simple closed geodesics and she showed that the number of simple closed geodesics of length utmost L is polynomial linear from exponential. There's polynomial. So there is so much of, the number reduces when you look at the simple closed geodesics. And she showed that it's of the order of L raised to 6G minus 6. 6G minus 6 is the dimension. So it grows. So in fact, she showed that it is asymptotic to a certain constant. And the constant depends on the hyperbolic structure that you put. Okay. So this is roughly her first result, her result. And now, since it has so many other different structures, as we saw, symplectic structure and the symplectic form, and raise the symplectic form to 3G minus D, you get a volume form and so on. So that's what she's doing here. She takes the symplectic form and integrating, raising to this and so on. So she is actually looking at, she's looking at a surface different from what I have described, what are called bordered Riemann surfaces boundary, modular space, and so she had done all this calculation, and she could actually get whatever Witten's conjecture. Witten's conjecture actually proved earlier by Kontsevich. Kontsevich is another Fields medalist. Okay, okay. So so he had proved this formula, and Mirza Zahani arrived at that formula through her calculations, which means she gave another proof of Witten's conjecture. It's not surprising really as such. So you can see that working bare hands with actual, the structure, the decomposition in a very systematic way, but of course it requires remarkable intuition. It's not just easy, putting together things. It requires a lot of intuition and diligence and tenacity, all of which Mariam Zahani certainly had. So now, how come Witten and physics come in here actually? Okay. So I just want to give a brief idea how physics could have come here is from the fact that essential point of string theory, which is one of those theoretical physics, the big theories, which is also for some time called as the theory of everything, because they really try to describe all forces of nature by this theory. So string theory, anyway, it has a lot of mathematical take on it, and one of the essential point of string theory is to replace point particle interaction. Instead of thinking of particle trajectory as a curve like this, point particle interaction by closed strings. So you don't think of it as a point particle, you think of it as a closed string, a circle. A circle moving in a straight line will give you a cylinder like this. Circle moving this along cylinder like this, but when they interact, you get something like this. So you can see this consists of two pairs of pants, for instance, if you cut along this here. Okay, so the point particle interactions were replaced by closed strings. So you really got these surfaces, okay, surfaces, and naturally because of interactions and so on, it led to the study of higher genus surfaces naturally, and because interactions and new particles coming in, various things. So as a result, so it's not surprising that Mirza Zahani's computations on this border Riemann surface had a bearing on Witten's conjecture. It's not surprising at all. So Mariam Zahani, in another direction, explored a relationship between what is called Thurston's earthquake flow on the Teichmüller horocycle flow. So I will not go into great detail about this thing. When you look at what is called the geodesic flow, it has a complementary flow called the horocycle flow, and one explored the dynamics of both, and Mirza Zahani really exploited the interplay of the dynamics of both these things. And she proved ergodicity of the earthquake flow on the modular space. This is another of her big results. And later, she explored the complex orbifold structure on the modular space, and she proved that the complex geodesics and their closures in modular space are surprisingly regular. I think at a certain point I mentioned earlier. So I'm not elaborate on this, but I hope I have been able to give you an idea of the kind of space that she is looking at and the way she is going about studying them. And because of the rich structure from different directions, so it's like it well to explore and the connections. You can really kind of explore and unravel some of these really the interplay. You can really unravel the way the different structures are connected by this method actually. So she really worked with bare hands, you can see. Okay, and this result with Alex Eskin and Amir Mohammadi actually sparked much excitement because, as I mentioned, it's a higher rank this thing, and rank one resonance with what called work of Ratner, Marina Ratner and Raghunathan's conjecture. That's another direction actually, but nevertheless, there in this particular thing you can have orbits which are fractal and so on. In fact, you can have orbits which are dense and closures to the whole thing and so on. We have a variety of orbits actually. But closure of what are called unipotent orbits have a certain, you can actually realize them as horocycle orbits actually. So in a sense, closure is again coming from another unipotent flow kind of thing. So that's Raghunathan's conjecture and Ratner's work on that. So these people worked on other version. This theorem of Mariam Zahani with all this called the magic wand theorem, because Ratner's work and Raghunathan's conjecture, the space, they're all it was a dynamics on what's called homogeneous spaces. Okay, whereas the moduli space in the case that these people were looking at is a totally inhomogeneous space. It must have been a lot of work for sure, and I think in the movie, the movie I mentioned by George Ciceri, actually Alex Eskin talked about the collaboration between them and how she was able to come up with certain very surprising techniques and so on, or ideas to connect things. So I'll not say more on that. Okay, so right now I'll just say, at least I tried to convey the power, or at least give a little idea of the kind of things she was dealing with. So the following statement made in her Fields Medal Award citation, really tells you the kind of range and the impact of her work. Let me just read it, the citation, her Fields Medal citation. It is astounding to find that the rigidity of homogeneous spaces has an echo in the inhomogeneous world of modular space. They're talking about the last work that I mentioned. Because of its complexities and inhomogeneity, moduli space has often seemed impossible to work on directly. But Mirzahani's strong geometric intuition allows her to grapple directly with the geometry of moduli space. In a remarkable range of mathematical techniques and disparate mathematical cultures, she of superb technical ability, bold ambition, far-reaching vision, and deep curiosity. I think all these statements really flowery, but really captures the essence of Mirzahani, I believe. Moduli space is a world in which many new territories await discovery. Mirzahani is sure to remain a leader as the explorations continue. Remember, this statement was made during her Fields Medal citation in 2014, when she was very much alive, but already kind of suffering. Alas, I mean, if you were alive, I'm sure things more greater things could have been there. So she has a picture of Mirzahani lecturing. And I show this picture basically because she's talking about that work on, this work that, with Eskin and Mohammadi. And she also mentions Moses and Shah. Shah was a dear colleague of us in TIFR. I mean, he is right now in the US. So I thought I'll mention that. I mean, there are people who worked on these things in our country as well. I just want to bring that sentiment as well. So this is her lecturing. So now that she is no more, the place where she studied, in Isfahan, a lecture hall is named after her in celebration of her. Though her living inspiration is not there, she inspires people through her work. And I thought I'll show this slide that the hall is named after Mirzahani. And so this is the front thing of the documentary by Ciceri, and this is a poster that the students made. So it's a celebration of the personality of Mirzahani. I think I'll end my talk here. This is my last slide, and I want to leave that screen with this slide. Yeah. Thank you. Should I stop screen screening, or I'll let, yeah, whatever, yeah, as you, yeah. Yeah. Let me stop sharing.
Thank you, sir.
Thank you.
For such an informative session on this works of Mariam Zahani.
Thank you.
And now I call upon Monica to propose formal vote of thanks.
Yeah. Okay. It gives me an immense, okay. It gives me an immense pleasure to propose vote of thanks of today's session on behalf of Department of Mathematics and Statistics. At the outset, I thank our today's resource person, Professor C.S. Arvindra sir, for accepting our invitation and inviting
Thank you.
us on the topic, the work of Mariam Zahani. Sir talked about Riemann surfaces, hyperbolic surfaces, and Mariam Zahani's main contributions on this. Now, I'm extremely thankful to Honorable Secretary, Professor K. Mutyam Reddy sir, Hyderabad Mahila Vidyalaya, and Secretary cum Correspondent, Professor G. Sudarshan Reddy sir, for the continuous encouragement in organizing the event. Now, I would also like to thank our principal, Dr. J. Achita Devi ma'am, for her constant support in organizing the program. A special thanks to Head Department of Mathematics and Statistics, Shweta Srivastava ma'am, for organizing the program. Finally, I would like to thank all the participants for the patient hearing and making the session a successful. Thank you, sir. Thank you so much.
Thank you. Thank you very much. Thank you very much, madam. Yeah. So if there are any questions, I can take. But I mean, of course, this, I believe it was sort of, it had some places where you can ask questions, and of course, places which may be inaccessible. So I apologize if the talk really, was not accessible, but I tried to convey some idea of Zahani's work. Yeah.
Your talk was very excellent, actually. I mean, I enjoyed it very much.
Oh, thank you, Archana. Yeah, how are you?
I'm good.
Okay. Thank you. Yeah, it's.
I mean, it was very surprising for me that I understood so much. Like, I attended Mirza Khani's lecture when I was in a student in 2010. Of course, I did not understand anything, but since she was so famous, we just went to see her like she's a celebrity.
Oh, yeah.
In ICWM, she lectured in University of Hyderabad in our auditorium.
Right, 2010. Okay, yeah.
Yeah, so we just went to see her. And your lecture was excellent. Thank you very much.
Thank you. Thank you so much. Yes. Yeah. Yeah. So shall I close the screen? Yeah, I suppose so. Yeah. I guess that's it, right? Yeah. Okay. Thank you.
Thank you, each and everyone. And we will join for the next session tomorrow at 3 p.m. by Professor Archana Mure Madam on the topic algebraic vector bundles. Thank you, each and everyone. Thank you.
Thank you.